this is not real. I don't believe it. I don't believe this exists. I'm so confused right now. What's up, guys, and welcome back to my channel. And if you're new here, then welcome to our little corner of the internet. Today we're going to be watching a video titled Hoover Dam, All the Secrets of the Engineering Wonder, which already by this first kind of frame, this looks insane. So yeah, without further ado, let's see what this is about.
The magnificent Hoover Dam, which was constructed 80 years ago, still stands strong and serves the U.S. in the fields of irrigation.
Wait, I went through all the emotions there. Those are cars going on top of that. Is that real? Like, is this something that's in real life? Do you drive across this? And it was constructed 80 years ago? Because this obviously isn't a real image. So what does it actually look like? Okay. Anyways, I'm asking way too many questions. I haven't even started the video.
U.S. in the fields of irrigation, flood control, and power production. Even during a torrential rainfall, you won't see Hoover Dam overflowing like this, causing destruction. Welcome to the engineering secrets of Hoover Dam. In this video, you're going to assume the role of Hoover Dam designer engineer Mr. John Savage and design and construct a gigantic dam in Arizona's Colorado River. Mr. John Savage's surveying team zeroed in on the Black Canyon Mountains beside the Colorado River. The reason? The mountains have a decent height and narrow gaps between them, allowing for huge savings on construction materials. However, many design challenges were still ahead of the project's chief engineer. Let's start with the design of a straight concrete wall of uniform width. The strong water pressure obviously causes the wall to deform and bend. You can observe that, due to this bending, the outer fibers become elongated and the inner fibers are compressed. This scenario results in tension on the wall's downstream side and compression on its upstream side. When tensile stress is applied to concrete, it easily develops cracks. Generally, modern buildings use steel bars to overcome this issue, as steel rods can readily carry a large tensile load. However, Mr. John Savage had a much simpler solution, one that does not require steel rods: the arch dam technology. When you give curvature to a dam, it becomes an arch dam. As shown, this arch dam deforms under the water loading. Now, if you compare this dam's deformed shape with its original shape, you'll notice that both the upstream and downstream fibers are undergoing a length reduction, which means the whole dam body will be under compressive loading. Concrete can withstand strong compression forces. This is the simple beauty of arch dam technology. However,
but what are these made for? To get power, or like I'm lost.
If we put the dam under service, it still has a good chance of toppling due to the water pressure. We can solve this issue by increasing the dam's width gradually toward the base. The approach will lower the dam body's center of gravity. The lower the center of gravity, the higher an object's stability. The design we achieved just now is called a gravity arch dam, and this design can overcome the issues of tensile stress and stability. This increasing width design can also resist shear forces. The water pressure diagram on the dam body is not uniform, but is triangular in shape and increases toward the base. However, since the area of the dam increases toward the base, the shear stress value at every cross-section is nearly identical. The next big challenge Savage faced was the height of the dam. The higher the dam, the greater its water storage capacity. This is obviously an advantage for electricity generation and flood control. But is it possible to construct a dam that is the same height as the mountain walls? First, we need to analyze the maximum flood discharge that can occur during the dam's lifespan, which depends on the regional rainfall data and catchment area. After constructing such a tall dam, even during a torrential river flow, if the dam is not getting filled to its capacity, then it has obviously been over-designed. Moreover, building a taller dam requires significantly more materials, drastically increasing its construction cost. Therefore, Mr. Savage selected a height that was cost-effective, meets the water demand of nearby cities, and also does flood control. The height he chose was 726 feet. The main design part of this dam is now complete. Now,
I would still make it taller just in case.
for the most interesting part, executing its construction. Being an arch gravity dam, it needs strong mountain walls to transfer the load. Let's take a
Oh yeah, and this one was massive. How do you build that? There was cars driving on top of it. That's wild.
cross-section of the
Humans
mountains.
are so weird.
You can see the rocks on the surface are weathered and quite weak. Therefore, the first task during the Hoover's construction was to remove all those weathered rocks until only the virgin ones remained. To reach the virgin rocks, the workmen drilled holes using jackhammers and blasted them using dynamite. After blasting, acrobatic workmen were sent with ropes to clear loose rock from walls, and the excavated material was transferred away via trucks.
I know this job is probably super dangerous, but that kind of sounds like a fun job. Like, you know, climb a kind of like mountain with a rope and then just clear rocks.
This dam should have a strong joint with the side walls. For this purpose, they excavated the mountain wall in the shape of an arch, again using dynamite explosion. The dam body takes form from these deep holes, making the mountain wall-dam connection really strong. Now, the next big question is how the ground will bear the weight of such a massive dam. When excavating, it is crucial to reach a strong layer of soil called hard strata. To find the hard strata, the workers used power shovels and excavated the riverbed till a depth of a whopping 135 feet. They excavated the riverbed in the same width as the base width of the dam.
I was like, why is there no water here? But wait, why is there no water? Is this like a human-made river? It wouldn't make sense, no. I'm so confused right now. How is there no water while they're working? What the hell? Anyways.
One detail we didn't mention yet is that before they began all this work, they had to first divert the river flow in another direction. To do so, they constructed temporary cofferdams and diversion tunnels. Now it's time for the concreting. For this, we must first arrange the formwork, which is made up of wood, for the concreting. Once the formwork or mold is done, we'll start pouring the concrete. However, the main issue here is that when cement reacts with water, it produces heat. Considering the scale of the project, pouring all the concrete at once will create an enormous store of heat, which will result in material expansion and thermal cracks in the concrete, making the project a failure. Here is a construction innovation to solve this issue. The engineers cleverly divided the entire dam area into a number of blocks, each approximately 50 by 50 feet, and poured concrete into each block mold work one by one. These small quantities of concrete took much less time to cool. In addition, they embedded 2-inch diameter steel pipes into these blocks. The pipes carried cool water, which controlled the temperature in the concrete and set it quickly and easily. Once the concrete hardened, workers...
It sounds like a lot of extra steps to me. Why wouldn't you just pour it little by little, just let it cool off, and then just pour some more? Would be way more cost effective too.
Filled these steel pipes with a grout cement slurry. This technique proved so effective that the Hoover Dam hasn't shown any cracks to date. Now, let's explore the details of Hoover Dam's biggest application, electricity.
I want to see what it looks like in real life though. Are they ever going to show what it looks like in real life? Because this is not real. I don't believe it. I don't believe this exists.
City production. You might have observed 4 huge towers inside the dam's water body. These are intake towers. Several gates along the height of these towers regulate water flow rate. The intake tower is then connected to these 500-foot-long penstocks that carry water to the turbines. To generate power, Mr. Savage designed a U-shaped power plant at the base of the dam downstream. Water from the penstocks turns 17 Francis-type vertical turbines, which rotate a series of electric generators. Each of these generators produces enough electricity to serve 100,000 people. Later, this water is released through outlets downstream for irrigation purposes. The Hoover Dam irrigates more than 1 million acres of land. Interestingly, the dam also creates one of the largest man-made lakes in the world, Lake Mead. This huge water storage facility helps groundwater recharge, thus increasing the water level in nearby wells. The next obvious application of Hoover Dam is flood control. In case of flood or heavy rains, the dam stores the water in the reservoir and prevents its flow from threatening the lives and structures in the downstream area. Now, let's consider a small design challenge. What if the dam overflows? It can easily damage the structures constructed downstream. To solve this potential problem, they constructed passageways called spillways on either side of the dam upstream so that water can be spilled downstream. These spills are located 27 feet below the top of the dam. If water reaches that level, it starts flowing into spillways. Did you know that you can actually walk inside the Hoover Dam body? Several tunnels are hidden inside the dam body. They have to construct these tunnels because of a simple phenomenon with which we're all familiar.
It looks very solid though, okay. It does look very, very solid. But it's still kind of nerve-wracking. I mean, imagine how much power this water has, like how much pressure it pushes into it. And it's been there for 80 years. Like, I would have maybe trusted these tunnels 10 years in, 15 years in, even 20 years in. But 80 years? Suspicious.
Water seepage. A liquid under pressure always wants to escape through porous material. Here, the water molecules flow through the soil below the dam body due to the seepage effect. The issue is that this flow generates a high uplift pressure on the base of the dam, drastically reducing its stability. This is why Mr. Savage designed a gallery, a tunnel that collects all seepage water from the dam body and base. This action reduces the uplift pressure considerably. The collected water is then discharged safely. The galleries also provide passageways for leak or crack inspections. Such detailed engineering plans with a future-focused vision are the reason why the Hoover Dam is still standing strong and serving the nation. We hope you enjoyed learning all about this engineering feat. Before the video ends, Lessix would like to pay homage to all 96 workers who sacrificed their lives to make this gigantic dam a reality. See you next time. Thank you for watching.
96 workers? That is wild and very, very sad. But yeah, I mean, the engineering is extremely impressive. And again, this makes me like think about how fun engineering must be when you're really into it, because you get to like look for solutions to, you know, issues and see how your image comes to life. I think is very, very interesting. But yeah, I'm upset that it didn't show any real photos of it. I'm gonna look up some photos of it now, because how do I know if it's real or not? If like why? Where's the evidence? So yeah, thank you guys for joining me for this video. I really hope you enjoyed it. Please leave your thoughts in the comments below. Leave a like, subscribe if you haven't yet, and I'll see you guys in the next video.